Today we are going to discuss chemical reactions of alcohol and phenols. So let's read from the book. Alcohols are versatile compounds. They react both as nucleophile and electrophile. The bond between oxygen and hydrogen is broken when alcohol reacts as a nucleophile. And here reaction is given when alcohol acts as a nucleophile. So let's examine the reaction. Here this is alcohol molecule in which oxygen has lone pair of electrons. Due to presence of these lone pair of electrons, alcohol acts as a nucleophile when it reacts with carbocation. Oxygen donates a pair of electrons to carbocation and make bond with it. As it donated a pair of electrons to carbocation, oxygen develops positive charge. To neutralize this positive charge, hydrogen leaves the molecule in the form of H plus ion. And here you will get the product of the reaction. Now let's see when it acts as an electrophile. In the second condition, when the bond between CO is broken, when they react as an electrophile. Protonated alcohol react in this manner. So here reaction is given when the protonated alcohol acts as an electrophile. Now let's examine the reaction. Here this is alcohol when it receives H plus ion from the medium and get protonated. It will form protonated alcohol. As the oxygen donated a pair of electrons to H plus ion, it will make bond with the H plus ion. And by the donation of electron, oxygen develops positive charge. Now this positively charged OH2 group, it will withdraw electron density from carbon more strongly than before. As it withdraws electron density from carbon, this carbon becomes electron deficient. Now this electron deficient center acts as an electrophile. So when Br negative comes in the medium, it will react with electron deficient carbon and expel the H2O positive ion in the form of water molecule, which is a good leaving group. And that's how protonated alcohol undergo nucleophilic substitution reaction. Now let's try to understand when alcohol acts as a nucleophile and acts as an electrophile. So this is alcohol. Let's draw the structure of alcohol. One of the alcohol, we can draw the structure of methanol. So this is CH3OH. And here also again I am going to draw the same structure, CH3OH. In alcohol, oxygen carries a lone pair of electron. Due to presence of lone pair of electron, it acts as a nucleophile because it can donate lone pair of electron to electrophilic center. As it is written here, the protonated alcohol acts as an electrophile. So let's see when this alcohol react with H plus ion. The oxygen has lone pair of electron, so oxygen will donate a lone pair of electron to H plus and make bond with it. So when it donated lone pair of electron to hydrogen, oxygen will develop positive charge. So here this oxygen will develop positive charge. Now this positively charged oxygen will become more electron deficient, so it will withdraw electron density more strongly than before. So this H2O positive ion has strong minus I effect. So by the strong minus I effect, it will withdraw electron density more strongly from the carbon next to it. So by the withdrawal of electron density from this carbon become electron deficient. So now this carbon become electron deficient. This electron deficient center acts as an electrophile. That's why it is written here that protonated alcohol acts as an electrophile. Now let's re-examine these reactions. So in the first reaction, when alcohol acts as a nucleophile, alcohol as nucleophile. Now the reaction is given here with the carbocation. So reaction that is given here with the carbocation. So here this is ROH. As we have already discussed, oxygen has two lone pair of electrons. when it reacts with carbocation. So this is C positive and there are 3 other valencies. So when alcohol react with carbocation, oxygen donate a pair of electron to carbocation and will make bond with the carbocation. So this is ROH, and now oxygen has made bond with the carbocation. As it has donated a pair of electron to carbon, oxygen will develop positive charge. Now to neutralize this positive charge, hydrogen leaves the molecule without its pair of electron. So here you will get the product RO. It is already bonded with a alkyl group which was carbocation, and now hydrogen has left the molecule in the form of H plus ion. So here you will get H plus ion. By the completion of this reaction, the bond between oxygen and hydrogen is broken. So that's why it is written here, when the bond between oxygen and hydrogen is broken, alcohol react as a nucleophile. So when alcohol acts as a nucleophile, bond between oxygen and hydrogen will break. Now let's see when alcohol acts as an electrophile. Here it is written that protonated alcohol acts as an electrophile. So here we can take the example RCH2OH. This is alcohol when it reacts with proton. Oxygen has a pair of electron, lone pair of electron, so it will donate a pair of electron to H plus ion and make bond with the H plus. So this is RCH2. It is bonded to oxygen and oxygen is bonded to 2 hydrogen. As oxygen donated a pair of electron to H plus, oxygen develops positive. Now this positively charged oxygen withdraw electron density from the carbon. As oxygen withdraw electron density from this alpha carbon become electron deficient. And this electron deficient alpha carbon act as a electrophile. So this electron deficient alcohol, this is RCH2OH2. This oxygen is positively charged. When it reacts with nucleophile, so I can take the example of Br negative ion, which is a nucleophile. As this carbon is electron deficient, this bromine will attack on this carbon and expel the H2O positive ion in the form of H2O. So here you will get the product R, and here bromine will get attached to CH2, so Br, and H2O positive ion is removed in the form of water molecule, which is a very good leaving group. So that's how it will undergo nucleophilic substitution reaction, in which protonated alcohol acts as an electrophile. Now let's read from the book. Based on the cleavage of OH bond and CO bonds, the reaction of alcohol and phenols may be divided into 2 groups. The first type of reaction involving the cleavage of OH bond. First reaction is given acidity of alcohol and phenol. So here we are going to discuss the acidity of alcohol and phenol. So let's read from the book. Reaction with metals. Alcohol and phenol react with active metals such as sodium, potassium and aluminium to yield corresponding alkoxide or phenoxide and hydrogen. First reaction is given ROH. It is an alcohol. When it reacts with sodium metal, it gives sodium alkoxide and hydrogen is removed in the form of hydrogen gas. In the next reaction, here tertiary butyl alcohol is given. When it reacts with aluminium, it forms aluminium tertiary butoxide and hydrogen is removed in the form of hydrogen gas. In the third reaction, phenol is given. When it reacts with sodium, it forms sodium phenoxide and hydrogen is removed in the form of hydrogen. Now let's try to understand how these reactions takes place. Here we are discussing the acidity of alcohol and phenols. So acidity of alcohol or phenols. First we are going to take the example of alcohol. So this is ROH. This is an alcohol. When it acts as an acid, means it will donate H plus ion. When H plus ion are removed from the molecule, it will form RO negative ion. This RO negative ion is called as alkoxide ion. This is alkoxide. So first we are going to discuss the reaction of alcohol with sodium. Sodium is electropositive element. It is a metal. Metals are electron donor. And sodium has one valence electron. When it reacts with H plus ion, so it will donate its one valence electron to H plus ion, and as a result of it, sodium will develop positive charge and H plus will become hydrogen. So this Na plus ion will make bond with the RO negative ion. Now let's write the reaction. So this is ROH. When it reacts with sodium, it will form RO negative, and this RO negative will get combined with the Na positive, and hydrogen is removed. But here, because hydrogen cannot be removed in the form of atomic hydrogen, that's why we have to take 2 moles of alcohol. To react with 2 moles of alcohol, 2 moles of sodium are required, and as a result of it, 2 moles of sodium alkoxide will be formed, and then you will get 1 mole of hydrogen gas. Similarly, when you write the reaction with aluminium, so here this is aluminium, its atomic number is 13. When you write the electronic configuration, you will get 1s2, 2s2, 2p6, 3s2, 3p1. So third shell is the valence shell, and how many valence electrons are there? There are 3 valence electrons. Means aluminium can donate 3 electrons to H plus ion. So means when aluminium react with H plus ion, it will react with 3 H plus ion, and as a result of it, you will get aluminium 3 plus ion and 3 hydrogens are formed. But there are 3 atomic hydrogen. Now let's write the reaction with alcohol. ROH, when it reacts with aluminium, it will form RO negative, and it will make bond with the aluminium plus 3. To balance the charge, you will require 3 moles of RO negative. Now 3H will be removed, but again hydrogen cannot be removed in the form of atomic hydrogen. It has to remove in the form of molecular hydrogen. To remove in the form of molecular hydrogen, you have to change the number of moles of alcohol and aluminium. For that, you will require 6 moles of ROH, because when 6 moles of alcohol will react, 6 moles of hydrogen will be removed, and this 6 moles of hydrogen can be converted into 3 H2 molecules. So that's why 6 moles of alcohol, when it react with 2 moles of aluminium, as 1 aluminium can donate 3 electrons, and here we require 6 electrons for 6 H plus ion. So that's why we have to take 2 moles of aluminium. When it react, it will form 2 moles of aluminium oxide, and that's how 3 moles of hydrogen will be removed. Now let's write the reaction with phenol. So this is benzene with alternate single and double bond, and when it is bonded to OH, it becomes phenol. When it reacts with sodium, in the same way, H plus will be removed from H plus will be removed, and that H plus will gain electron from sodium, and this phenoxide ion will be formed, which will make bond with the Na plus ion. This is O negative. This O negative ion is called as phenoxide. This phenoxide will make bond with the sodium. So that's why the name of this molecule will be sodium phenoxide. because first we write the name of positive ion, then we write the name of negative ion. That's why the name of this molecule will be sodium phenoxide, and hydrogen will be removed in the form of H2. To remove 2 hydrogen, we have to take 2 moles of phenol, and to react with 2 moles of phenol, you will require 2 moles of sodium, and here you will get 2 moles of sodium phenoxide, and then 1 mole of hydrogen will be removed. Now let's read from the book. In addition to this, phenol react with aqueous sodium hydroxide to form sodium phenoxide. Let's examine the reaction. Here this is phenol when it reacts with sodium hydroxide. As we are discussing the acidic nature of alcohol and phenol, so this acid can react with base. NaOH is a base, so it can react with a base, and as a result of it, salt is formed, which is sodium phenoxide, and water is removed from the molecule. So here when you see the reaction, so let's try to write the reaction. This is phenol. Benzene with OH is called phenol when it reacts with NaOH. So phenol will donate H plus ion and sodium hydroxide will donate OH negative ion. So this H plus and OH negative will get combined together and form water molecule, and phenoxide ion will get combined with the Na plus ion. So here you will get sodium phenoxide. This O negative ion will get combined with the Na positive ion, and that's how sodium phenoxide and water molecules are formed by the reaction of phenol and sodium hydroxide. In the above reaction shows that alcohol and phenols are acidic in nature. In fact, alcohol and phenols are Bronsted acid. That means they can donate proton to a strong base. Means when they react with NaOH or active metals, they donate H plus ion to them and they form conjugate base. So let's try to understand it. This is ROH. This is an alcohol. So when it react with base, it donate its H plus ion. So when it donate its H plus ion, so base will make bond with the hydrogen and RO negative ion will be formed. So here this alcohol acts as a Bronsted acid. This is Bronsted acid, and after donating the H plus ion, it will form its conjugate base. Similarly, you can write the reaction with phenol. When phenol react with base, it will donate H plus ion to base and it will form phenoxide ion. So this is phenoxide ion, and this phenoxide ion is a conjugate base. Now let's read from the book Acidity of Alcohol. The acidic character of alcohol is due to the polar nature of OH bond. An electron releasing group CH3C2H5 increases electron density on oxygen, tending to decrease the polarity of OH bond. This decreases the acidic strength. For this reason, acidic strength of alcohol decreases in the following order. This is primary alcohol, this is secondary, and this is tertiary alcohol. Primary alcohol are most acidic and tertiary alcohol are least acidic. So let's try to understand it and draw the structure of primary alcohol. R CH2, it is bonded to OH. OH is the functional group and the carbon to which this is bonded is called alpha carbon. This alpha carbon is bonded to one of the alkyl group. So that's why this alcohol is called as primary alcohol. In this primary alcohol, the alkyl group donate electron density through plus I effect. By the donation of electron density through plus I effect, this alpha carbon become electron rich. Now this electron rich alpha carbon donate electron density to oxygen. Now this oxygen, because it has gained electron density from the alpha carbon, it will withdraw less electron density from hydrogen. That's why the bond between oxygen and hydrogen become less polar. Now when you examine the secondary alcohol, In secondary alcohol, there are two R groups bonded to alpha carbon, and this alpha carbon is bonded to OH. Now, this alpha carbon is even more electron rich by the donation of electron density through 2 plus I effect of two alkyl groups. Now, this more electron rich alpha carbon donate electron density to oxygen. Now, this oxygen will gain more electron density from the alpha carbon, so it will withdraw even less electron density from the hydrogen. That's why this secondary alcohol will become less polar than before. As it becomes less polar, there will be less possibility to remove hydrogen in the form of H plus ion. When you examine tertiary alcohol, in tertiary alcohol there are 3 R groups bonded to alpha carbon, and this carbon is bonded to OH. So as it receives electron density from 3 plus I effect of 3 alkyl group, this alpha carbon will become more electron rich, and when it supply electron density to oxygen, as the oxygen gains sufficient electron density from the alpha carbon, it will withdraw even less electron density from hydrogen. So in case of tertiary alcohol, there will be very less chances of removal of hydrogen in the form of H plus ion. So there will be very less probability of removal of hydrogen, this hydrogen in the form of H plus ion, because the bond between O and H become least polar. That's why the acidic character of tertiary alcohol will be least among them, and primary alcohol will be more acidic among them. Now let's read from the book. Alcohols are, however, weaker acid than water. This can be illustrated by the reaction of water with an alkoxide. When alkoxide ion react with water molecule, it abstract H plus ion from the water molecule, means water has donated H plus ion to alkoxide ion, means here water act as an acid while alkoxide ion act as a base. As it receive H plus ion from the water, it forms conjugate acid. So this is the conjugate acid, and as water removes H plus ion, OH negative ion will be the conjugate base of water molecule. This reaction shows that water is a better proton donor than alcohol. Also in the above reaction, we note that alkoxide ion is a better proton acceptor than hydroxide ion, which suggests that the alkoxide are stronger base. Because the reaction is unidirectional, when you see the direction of the reaction, this is unidirectional reaction. That means when hydroxide ion react with alcohol, it won't be able to abstract H plus from the alcohol molecule, as the hydroxide is a weak conjugate base of water. Weak conjugate has a strong component. As the conjugate is weak, its acid will be strong. That's why water is a strong acid. And when you see this alcohol cannot release H plus ion to hydroxide, means this conjugate is a weak conjugate, and as it is a weak conjugate, alkoxide ion will be the strong base. So when you compare the acidity of water and alcohol, you will see water is a stronger acid than alcohol, and when you compare the basic strength of alkoxide and hydroxide, you will see alkoxide is a strong base as compared to hydroxide. Alcohol acts as Bronsted base as well. It is due to the presence of unshared electron pairs on oxygen, which makes them proton acceptor. So alcohol acts as a Bronsted base as well, because it can abstract H plus from the molecule, and we have seen the protonation of alcohol. Let's revise the thing that we have discussed earlier when we have seen the reaction of alcohol with H plus ion. When you have seen the reaction of alcohol with H plus ion, I told you oxygen carries 2 lone pair of electrons, and it can donate lone pair of electrons to H plus ion, and it can make bond with it. And here you will get protonated alcohol. This is RO. It is bonded to 2 hydrogen. As this oxygen donated a pair of electron to H plus ion, it will develop positive charge, and this is protonated alcohol. Here when you re-examine the reaction, in this case alcohol accept H plus ion, means this alcohol act as a Bronsted base. And this protonated alcohol will become conjugate acid of alcohol. Now let's read from the book Acidity of Phenol. The reaction of phenol with metals, for example sodium aluminium and sodium hydroxide, indicate its acidic nature. Hydroxyl group in phenol is directly attached to sp2 hybridized carbon of benzene ring, which act as a electron withdrawing group. So this sp2 hybridized carbon of benzene act as a electron withdrawing group. Due to this, the charge distribution in phenol molecule as depicted in its resonance structure causes the oxygen of OH group to be positive. So let's draw the resonating structure of phenol for the better understanding. This is benzene, and here this is oxygen bonded to hydrogen. As this carbon make 3 sigma bonds, so this carbon has made 3 sigma bonds and 1 pi bond. Because of the formation of 3 sigma bond, the hybridization of this carbon will be sp2, and you know the electronegativity order of carbon. So sp hybridized carbon is most electronegative, then sp2 hybridized carbon, and sp3 hybridized carbon is least electronegative. So that's why it is written there that sp2 hybridized carbon is electronegative and it can withdraw electron density. So let's draw the resonating structure of phenol. So you know this sp2 hybridized carbon can withdraw electron density. So this is oxygen bonded to hydrogen. Oxygen has 2 lone pair of electron, and as you seen here, this sp2 hybridized carbon act as a electron withdrawing group. This sp2 hybridized carbon will withdraw electron density from carbons. So these lone pairs will move between carbon and oxygen, and the pi bond will move to the next carbon. So here you will get the next resonating structure. These 2 bonds will remain as it is. Between carbon and oxygen, one more bond will be formed. As oxygen donated a pair of electron to carbon, this oxygen will develop positive charge, and the pi bond move to this carbon in the form of negative charge. Now draw the next resonating structure. In the next resonating structure, this negative charge will move between these 2 carbon in the form of pi bond, and this pi bond will move to the next carbon in the form of negative charge, and rest of the structure will remain as it is. So here there are double bond between carbon and oxygen. This oxygen has positive charge, this bond will remain as it is, and here new bond will be formed at this position, and that pi bond move to the carbon in the form of negative charge. Now draw the next resonating structure. In the next structure, this negative charge will move between these 2 carbon in the form of pi bond, and the pi bond move to the next carbon in the form of negative charge. So here you will get the next resonating structure where new bond is formed between these 2 carbons, and pi bond move to the carbon in the form of negative charge, and rest of the structure will remain as it is. This oxygen already has positive charge, and this bond will remain as it is. Now you can draw the next resonating structure in which this negative charge move between these 2 carbon in the form of pi bond, and the double bond move and neutralize the charge over oxygen. So here you will get the next resonating structure. These 2 bonds will remain as it is, and new bond is formed between these 2 carbons, and this time oxygen carbon bond will become single bond, and the charge over oxygen again neutralizes. So that's how you will get these many resonating structures. So these resonating structures are interconvertible to each other. Now let's read from the book. The reaction of phenol with aqueous sodium hydroxide indicates that the phenols are strong acid than alcohol and water. The reaction of phenol with aqueous sodium hydroxide indicates that phenols are stronger acid than alcohol and water. Because only phenol can react with aqueous sodium hydroxide, alcohols do not give any reaction with aqueous sodium hydroxide. So here you can just remember, phenol can react with aqueous NaOH and form sodium phenoxide and water. While alcohol do not give any reaction with NaOH, aqueous NaOH. It do not give any reaction. By this reaction you can differentiate between phenol and alcohol. Now let's read from the book. Let us examine how a compound in which hydroxyl group attached to an aromatic ring is more acidic than the one in which hydroxyl group is attached to an alkyl group. Means we are going to compare the acidic character of phenol and alcohol. Why phenols are more acidic? So here, by the evidence of reaction with NaOH, phenols are more acidic than alcohol. So we are going to discuss the reason behind it, why phenols are more acidic than alcohol. The ionization of alcohol and phenol takes place as follows. Here it is given, this is alcohol. When H plus is removed from the molecule, it will form alkoxide ion and H plus ion. And in case of phenol, when ionization takes place, it dissociates into H plus ion and phenoxide ion. Due to higher electronegativity of sp2 hybridized carbon of phenol to which OH is attached, electron density decreases on oxygen. This increase of polarity of OH bond results in increase in ionization of phenol than the alcohol. So this is the first reason. So let's try to understand the reason. This is phenol, benzene ring with alternate single and double bond. Here this is OH. When it ionizes into phenoxide ion. This is benzene to which O negative ion is bonded, and here this is H plus ion. The carbon to which oxygen is bonded, we have already discussed the hybridization is sp2, and this sp2 hybridized carbon is more electronegative, means it will withdraw electron density from oxygen. So when it withdraw electron density from oxygen, ultimately oxygen will withdraw electron density from hydrogen. So here when you see the withdrawal of electron density, this carbon withdraw electron density from oxygen. Ultimately this oxygen will withdraw more electron density from hydrogen. So the bond between oxygen and hydrogen, this bond will become more polar. As this bond become more polar, it is easier for the hydrogen to leave the molecule in the form of H plus ion. So that's why the removal of H plus ion become easier because of this sp2 hybridized carbon to which oxygen is bonded, the removal of H plus ion is become easier. While in case of alcohol, this is RCH2OH. Here the carbon to which, so in case of alcohol, the carbon to which hydroxyl group is bonded has formed 4 sigma bond, and for the formation of 4 sigma bond, hybridization will be sp3. And I told you earlier, sp3 hybridized carbon is least electronegative, so it won't be able to withdraw electron density from the oxygen. Instead, it donates electron density to oxygen. Because of that, the polarity between oxygen and hydrogen decreases. So this bond will become less polar. As the bond between oxygen and hydrogen become less polar, it makes the removal of H plus ion difficult. So removal of H plus ion is difficult. in case of alcohol, while it is easier in case of phenol. Now let's read from the book. Due to higher electronegativity of sp2 hybridized carbon of phenol to which OH is attached, electron density decreases on oxygen. This increases the polarity of OH bond and results in increase in ionization of phenol than that of alcohol. Now let us examine the stability of alkoxide and phenoxide ion. In alkoxide ion, negative charge is localized on oxygen, while in phenoxide ion, the charge is delocalized. Now let's draw the resonating structure of phenoxide ion. So this is phenol, benzene ring to which OH is bonded is phenol. When it donates H plus ion, oxygen will acquire negative charge and H plus is removed from the molecule. So this is phenoxide. This is phenoxide ion. Now let's draw the resonating structure of phenoxide ion. As we have drawn the structure of phenol. So this is phenoxide O negative. Now this negative charge moved between carbon and oxygen, and the pi bond is moved in the form of negative charge to the next carbon. So here you will get the next resonating structure. In this structure, this carbon oxygen bond will become double and the charge over oxygen neutralizes, and this pi bond move to the ortho position in the form of negative charge. In the next resonating structure, this negative charge moved between these two carbon in the form of pi bond, and this pi bond moved to the next carbon in the form of negative charge. In the next resonating structure, these two bonds will remain as it is. New bond will be formed between these two carbon and pi bond move to the para position in the form of negative charge. Now in the next resonating structure, this negative charge move between these two carbon and this pi bond move to the next carbon in the form of negative charge. So here let's draw the next resonating structure. In the next resonating structure, these two bonds will remain as it is, and new bond will be formed here, and negative charge will develop at the ortho position. So when you see the delocalization of negative charge, in the first structure negative charge is over oxygen, in the second it moved to the ortho position, in third it moved to para position, and in fourth structure it moved to again ortho position. So means there is delocalization of negative charge. While in case of alkoxide ion, so when you draw the structure of alkoxide, this is R group, CH2OH, this is alcohol. When it donates H plus ion, it will form alkoxide ion. So RCH2O negative ion, this is an alkoxide ion, and this is H plus ion. So in this alkoxide ion, the alkyl group donate electron density through plus I effect, and this alpha carbon ultimately donate electron density to O negative ion. So by the donation of electron density through plus I effect, actually it destabilizes the alkoxide ion. So that's why this alkoxide ion is unstable, while the phenoxide ion is more stable as compared to alkoxide ion, as we have discussed earlier. Now let's read from the book. Phenoxide ion is more stable and favors the ionization of phenol, although there is also charge delocalization in phenol. Its resonance structure have charge separation, due to which the phenol molecule is less stable than the phenoxide ion. So when you examine the resonance structure of phenol and phenoxide ion, in case of the resonance structure of phenol, when you see the resonance of phenol, there is charge separation. In first molecule there is no charge, while in the resonating structures there is charge separation. Means there is positive charge and negative charge in the molecule. Because of this charge separation, phenol is unstable, while in case of phenoxide ion, there is delocalization. Because of the delocalization of charge, this phenoxide ion is more stable as compared to phenol. So here, when you compare between phenol, when it ionizes, it will form phenoxide and H plus ion. So here it is written that phenoxide ion is more stable by the delocalization of charge, and phenol is less stable because of separation of charges. As phenol is less stable, means it favors the ionization or the removal of H plus ion. Now let's read from the book. In substituted phenol, the presence of electron withdrawing group such as nitro group enhance the acidic strength of phenol. This effect is more pronounced when such groups are present at ortho or para position. This is due to the effective delocalization of negative charge in phenoxide ion when substituent is at ortho or para position. On the other hand, electron releasing group such as alkyl group in general do not favor the formation of phenoxide ion, resulting in decrease in acid strength. Cresol, for example, is less acidic than phenol. So this is phenol. And here oxygen is bonded to hydrogen. So if the electron withdrawing groups are present at ortho position, here electron withdrawing group, and here also one electron withdrawing group, and if here also electron withdrawing group is bonded. So these electron withdrawing groups will withdraw electron density from oxygen. So when they withdraw electron density from oxygen, they will increase the polarity of hydrogen-oxygen bond. So due to presence of electron withdrawing group, the polarity increases. Polarity increases. Due to increase in polarity, removal of H plus ion will become easier. That's why the presence of electron withdrawing group at ortho or para position increases the acidic strength of phenol, while in case of electron donating groups. So now let's draw the structure of phenol with electron donating groups. So here this is OH, this is phenol. If electron donating groups are bonded to ortho or para position, electron donating groups. Here electron donating groups are bonded. If these electron donating groups are bonded to ortho or para position, they will donate electron density to oxygen. So by the donation of electron density from electron donating groups, the polarity of oxygen hydrogen bond decreases. So this bond will become less polar. As it becomes less polar, the possibility of hydrogen to remove in the form of H plus ion decreases. That's why if electron donating groups are bonded, it decreases the acidity of phenol, while electron withdrawing group increases the acidity of phenol. Now let's examine the table 7.3. Here pKa value of some phenol and ethanols are given. And side note is given, the greater the pKa value, weaker the acid. Means if the pKa value is more, acid will be weak. So let's see which of the following will have least pKa value. Here you can see 7.1 is the least one, and it is for the para-nitrophenol. Means if the nitro group bonded to para position, that phenol will be more acidic among them. And for ethanol, pKa value is 15.9, which is the highest among them. Means ethanol is the least acidic and para-nitrophenol is most acidic among them. From the above data, you will note that phenol is million times more acidic than ethanol. Now come to the example 7.4. Arrange the following compounds in increasing order of their acidic strength. Propane 1-ol, 2,4,6-trinitrophenol, 3-nitrophenol, 3,5-dinitrophenol and 4-methylphenol. So let's draw the structure of these molecules. First one is propanol. So CH3, CH2, CH2OH, this is propanol. The next one is 2,4,6-trinitrophenol. So first of all, draw the structure of phenol. Here OH is bonded to first position, second, fourth and sixth position nitro group is there. So this is first, second, third, fourth, fifth and this is sixth. Here nitro group is there, NO2. Next is Next is 3-nitrophenol. So this is phenol. At third position nitro group is there, NO2. Then 3,5-dinitrophenol. This is OH, NO2 here and here. Then 4-methylphenol. The last one is 4-methylphenol. Here CH3 group is there. Here we have to arrange them in increasing order of their acidic strength. So propanol will be the least acidic as it is alcohol. It will be least acidic. Now we have to compare between the phenol derivative. Nitro groups are electron withdrawing groups. Here these are the nitro groups, so they all are electron withdrawing group, means they will increase the acidity of phenol. But here this methyl group is electron donating group. So this electron donating group decreases the acidity of phenol. It decreases the acidity of phenol. So after alcohol, 4-methylphenol will be there. It will be more acidic than alcohol. Though it will be more acidic than alcohol, but it will be less acidic than phenol. Now we have to compare between these three structures. Here there are 3 nitro groups bonded to 2 ortho and 1 para position. So they will withdraw electron density more strongly from OH and make it most acidic. So this one will be most acidic. There is just 1 electron withdrawing group that is bonded to meta position, and there are 2 nitro groups bonded to meta position. So these 2 electron withdrawing group will make phenol more acidic as compared to just 1 electron withdrawing group bonded to phenol. So let's number it. This is 1, 2, 3, this is 4th, this is 5th, and phenol will be the 6th one. Now when you arrange them in increasing order, so 1 means propanol will be the least acidic. Then after propanol, 4-methylphenol will be less acidic than the phenol, as there is electron donating group bonded to para position. So after propanol, 5th structure will be there, then phenol. After phenol, the nitro group, after phenol, the prophenol will be there, as there is just 1 electron withdrawing group bonded to phenol. After that, the 4th structure will be there, in which 2 nitro groups bonded to phenol. So there will be 3,5-dinitrophenol, and after that 2,4,6-trinitrophenol will be there. So here 2,4,6-trinitrophenol will be there. Now let's see the solution. In the solution also it is given propane 1-ol, then 4-methylphenol, then phenol. Due to the presence of electron donating group, methyl group is there, it will have less acidic strength than phenol. Then 3-nitrophenol, with just one nitro group bonded to phenol. Then the 3,5-dinitrophenol, due to presence of 2 nitro groups, it will be more acidic than the phenol with just one nitro group. And here with the 3 nitro groups, it will be most acidic. In the next video, we will discuss the next reaction, that is esterification.